Okay, so we're going to continue our basic development of connectivity with a couple of new concepts here. Uh, we're going to start off with the fairly basic notion of deletion. So if I give you a graph G, and first I'll give you a subset of edges. Then we can make a new graph from G, a subgraph of G, in fact, by taking the graph G, keeping all the vertices we have, deleting the edges that are in S, so you just keep the edges that are not in S, and you keep the same incidence relation that you had on the existing edges. So G minus S, this is going to be the graph obtained from G by deleting every edge in S. Right, so again, this new graph G delete S, it has all the same vertices as the original graph. It has all of those edges that are not in S, and the incidence relation on it is just the same as it was before, except that you now are missing the edges that you deleted. So the incidence relation on the existing edges is the same as it was before. Similarly, so I'm kind of defining a new thing here. Well, we're defining G delete S here. And similarly, if I give you a subset of vertices, we can make a new subgraph by deleting them. If I give you X as a subset of vertices of G, then G delete X, so I'm just writing it as G minus X. This is the new graph that you obtain from G by deleting every vertex in X and every edge that's incident with some vertex in X. So this is the graph obtained from G by deleting. Again, you're going to delete every vertex in X. And every edge incident to a vertex X. I hope this strikes you as a very sensible definition, right? If you want to delete a vertex, then all of the edges that are incident with that vertex are suddenly going to stop making sense as edges. They're not going to be behaving according to the same rule as they were before. So if you want to kind of have a subgraph and preserve your same incidence pattern, if you delete a vertex, you have to delete any edge incident with it. So I'm defining G delete S and G delete X. They're two tiny bits of just sort of shorthand here. If we have just a single edge E or just a single vertex V, then it's annoying to have to write the curly braces around it to delete just that vertex or just that edge, right? So I've defined formally here a way of taking a graph G and making a new graph. This new graph is always going to be a subgraph, and we've defined it by either deleting a set of vertices or a set of edges. And anyway, we'll just add a little bit of shorthand here. If I gave you a single edge E, or I give you a single vertex, V and V of G, we define G delete E to be G minus the set E. Or G delete V is G delete the singleton V. Sorry that my curly braces aren't a little better looking there. What am I doing? So if I want to take a graph and delete a single vertex v, I can just write g minus that vertex v. Or if you want to delete a set of vertices x, fine, g minus that set x deletes all those vertices. And as well, whenever you delete a vertex, you delete all incident edges. So this is a fairly natural concept. In fact, I even start saying this as soon as I say subgraph, because it's how we think of getting a subgraph. So formally, we've defined a subgraph as, we have a formal definition of it. It's a subset of vertices, subset of edges, same incidence relation. But the main way we think about getting subgraphs is just deleting. And this is the generic way, in fact, that you get a subgraph. So we can always think about them in this manner. Right, okay, so that's our concept of deletion. Putty cat. Sorry about that. Where am I? Right, okay. And next up, I want the notion of a cut edge of a graph. So you can define this two ways. I'm about to give you a proposition that gives us a couple of equivalent ways of saying the word cut edge. But just sort of for simplicity here, I'm going to define it with the sort of shortest sentence I can. So if I give you a graph G, E in E of G is a cut edge if there's no cycle that contains E. Okay, so as I said, we're about to get we're about to get some equivalences here. And let's right, let me just start. So what does it mean that you have an edge E that's a cut edge? Well, I mean, somehow, like, sort of pictorially, what's going on is, well, you're going to have a hunk of graph here and a hunk of graph here, and E is going to be the only edge going from the left to the right, right? So there will be a partition of the vertices into two sets, so the E is the only edge going left to right. That's, in fact, what a cut edge is going to be. You can, if you think about that picture for a moment, I think you'll realize that in that case, there will not be a cycle that contains the edge E. And in fact, when there is no cycle containing the edge E, that is indeed the picture that you have. There's going to be a partition of the vertices into two sets, so that E is the only edge going from one to the other. We're going to sort of prove this in the setting of components, right? So we already understand how the components of the graph work, right? You know that anytime you're given a graph, there's always a partition of the vertex set, blunk, 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 into components, into connected components. And so the way this works is that if you have any two vertices in the same connected component, then there's a walk from one to the other. If you have any two vertices in distinct components, then there's no walk from one to the other. In fact, when you look at the components of the graph, there are no edges of the graph that go from one component to the other. So the connected components are all connected little hunks of graph, and there are no edges in between them. Anyway, so that's components again. Let me say what we're going to prove now. So if I give you a graph and I give you an edge of the graph, one of two things happens. Then exactly one of the following holds. So either this edge E is a cut edge, and when you delete it, the number of components of the graph goes up by 1. right? So in our picture, you want to imagine your graph, maybe you have many different components. Maybe the edge E is a cut edge and it lives in this component. If it's a cut edge of this component, then what's going to happen is that when you delete it, suddenly you have two components there instead of one, so the number of components is going up by one. The second possibility is E is not a cut edge. If E is not a cut edge, then when you delete it, the component structure doesn't change. Every vertex is in the same component that it was before. So in that case, the number of components of G minus E is equal to the number of components of G. Excuse me. Right, so this is our last proposition. This is a fairly straightforward thing to prove. We're going to prove a kind of chain of a very simple chain of equivalences, and that will allow us to observe what's happening. I think once again, I'm not going to write everything here that's in the notes. I'm going to gesture a little and describe, and you can look to the notes if you want to see the full proof. So let's prove. So if I tell you E is, actually let me save as much space as I can here. So if I tell you E is not a cut edge, by definition, that is if and only if no sorry, that's if and only if there is a cycle containing E. Oh, sorry, what am I saying? Sorry, if E is not a cut edge, then that means there is a cycle containing E. Let's sorry, let me suppose here that E has ends. Sorry, I don't have a lot of space right now. I want to suppose, let me just insert a little. Suppose E has ends, let's say little x and little y. Okay, so my edge E is two ends, x and y. By definition, E is not a cut edge, if and only if there's a cycle containing that edge, E. Now, if there's a cycle containing the edge E, then when you delete the edge E from the graph G and delete the edge E from that cycle, what do you have? Well, if you take a cycle, here's the edge E with ends x and y. If you delete that edge, what are you left with? Well, you're left with a path from x to y. Right? So saying that you have a cycle containing the edge E in the graph G is exactly logically equivalent to the statement that there's a path in the graph G delete E between the two ends of that edge. So again, the statement that in the graph G you have a cycle containing the edge E is exactly equivalent to the statement that after you delete the edge E in that graph G delete E, you have a path from x to y, from one end of that edge to the other, right? If I give you a path from x to y in the graph G delete E, Well, then if you add the edge E back to that path, suddenly you've got a cycle containing E. And conversely, if you have a cycle containing E, then when you pluck that edge out, what you're left with is a path from X to Y. So again, we've learned that E is not a cut edge if and only if there's a path from X to Y between its ends in the graph G delete E. And that's equivalent to the statement that X and Y are in the same component of G delete E. So I'm going to draw the graph G delete E here. And there are two cases. So case one here is E is a cut edge. If E is a cut edge of the graph G, then what that means is that there is no path in G delete E between the two ends of that edge E, between X and Y. And that means that X and Y are in separate components. So just sort of pictorially here, in the graph G delete E, this is what you're going to see. Here's X and here's Y. Case 2 is cut edge. If E is a cut edge in G, then in the graph G, X and Y are, sorry, in the graph G delete E, X and Y are still in the same component. Right? So again, our two cases, if E is a cut edge of your graph G, then in the graph G delete E, there will be no path between its two ends, X and Y, and that means that X and Y are going to be in separate components, and that's the picture I've drawn. So if you have a cut edge, then the two ends of that edge are in separate components when you delete the edge. That's case 1. Case 2 is you do not have a cut edge. If you do not have a cut edge, then when you delete that edge, X and Y, there's going to be a path between X and Y, and that means that X and Y are still in the same component. And with this, we can complete the proof, which I'm now going to do just in words. So if we are in the first case and you have a cut edge, then what's happening is I have in G delete E, X and Y are in two separate components. That means when you move from G delete E back to the original graph G by adding back the edge E, you have a component here, you have a component here, and you're adding back one edge in between them. That's going to give you one new, so those two components are going to merge when you go back to the original graph, right? Because what's going to happen, they have this connected component and this connected component in G delete E. When you add the edge E back, suddenly this whole thing is going to be a giant connected subgraph, and that's going to be a component of the graph G. So if you have a cut edge, if E is a cut edge, then G delete E is going to have one more component than does G. Conversely, if you have an edge that's not a cut edge, then when you delete this edge E, X and Y are still in the same component of G delete E, and when you add the edge E back, it's not changing the component structure at all. So you have some little connected graph here, and you're just adding an edge back with both ends in that connected graph. That's just it's enlarging the component a little bit. That component will have one more edge, but it won't have any but there's no difference in terms of the set of vertices. So that means the number of components won't change. So again, the big take home here, the sort of simple message, if I give you an edge in the graph, there are two things it can do. Either you can draw me a picture where you show me where you partition the vertices into two sets, and this is the only edge going left to right. In that case, this edge is going to be a cut edge, and when you delete it, you're going to increase the number of components by 1. The other case is there's no such drawing. And in that case, you're going to have a cycle containing your edge E, and when you delete it, the number of components doesn't change. Okay, so that's going to complete this first sort of mini section on connectivity. As I said, we'll come back and do more with connectivity later in the course, but for now we're going to kind of step along and establish a few more kind of very basic graph theoretic principles, and that's what we'll do next. So that's it for this one.